All right, today we're going to look at Torricelli's law, which is a very special case for Bernoulli's principle or Bernoulli's law. And so for Torricelli's law to work, it must be an open container that has some hole or a spigot somewhere along the side, so that there's some amount of water above that hole. Water will come out of the hole of an open container at the same speed that a drop is dropped from the same height. That's Torricelli's law. So it says that if you took a droplet of water and you dropped it all the way down to a certain height, that the speed at that location is exactly the same as the speed of water exiting some hole. That those are going to be exactly the same speeds. So you can look at this with kinetic energy, but the main thing is to look at it using Bernoulli's principle, which says that the amount of pressure is constant. Essentially, we have this conservation of energy over volume. And so when we write out Bernoulli's principle, or Bernoulli's law here, we have the pressure at our first location, the gauge pressure, plus rho GH at our first location, plus 1/2 rho V squared, is going to be constant no matter where we pick. So we're going to pick a secondary location, and we're going to do exactly the same thing. So we have the pressure at location 2 plus rho GH2 plus 1/2 rho V2 squared. So our first location is going to be at the top, where it is still water at the top. If there is still water, that means that the initial velocity at the top has to be 0. So that whole term just goes away. We're going to pick some secondary location. So let's say we picked location C. That's our second place. If location C is our second place, then that is where we're going to set 0. So that's our lowest height. So at that location, we have no gravitational potential energy over volume, so that goes away. So now we have the pressure is equal to rho GH. The pressure plus rho GH is equal to the pressure at the second location times 1/2 rho V squared. And so if you're thinking about this container in itself, the pressure at 1 is 1 atmospheric pressure. And down at our second location, it's going to be, slightly different, but for all intents and purposes, it's open to the air. So it is also 1 atmospheric pressure. So because of that, we can say that there is a negligible difference between the two pressures. One atmospheric pressure. So we're really left with this equation, that rho GH, where H is going to be the difference between the top of the water and our location. So this is our H, is equal to 1/2 rho V2 squared. And that would just be our velocity exiting. Well, we do know that in this equation, density, if we divide by density, that goes away. All we have to do now is multiply by 2, so we have 2GH is equal to V squared. You just take the square root of both sides, which tells us that the velocity of the water leaving that location is equal to the square root of 2GH. Now, we know that an object dropped from a certain height, so if we look at the energy here, if it's dropped from here, it has all gravitational potential energy. And then when it gets down to this location, all that gravitational turns into kinetic. So if we do that same thing where we have the gravitational is equal to the kinetic energy of our dropped, droplet, dropped from that same height, then we have mgh is equal to 1/2 mv squared. You might notice this looks very similar to what we just did, except instead of having the density, we are given the mass. Just like before, mass will cancel out. So then we have, multiply by 2, we have 2gh is equal to v squared. Take the square root, and we have that the velocity is the square root of 2gh. Now, obviously, this is the velocity of the droplet, which is going directly down. This is the velocity of the particle leaving the container, which is actually going to the right or to the left, depending on which way it's facing. But if you look at the equations, they are identical in that you have exactly the same formula. It is the square root of 2gh. This is what Torricelli's law says. That water will come out of a hole in an open container at the same speed as a drop dropped at the same time from the same height. All right, let's do an example. A water droplet falls from rest from height h. So water droplet is dropped from rest of height h. So same height as this part over here. How fast is the droplet going compared to the speed of the water rushing out of the bottom of the container? So we want to say, how is the speed of our droplet compared to the speed of the water going out? Well, Torricelli says they are going exactly the same speed, which would be c. The next example says a container of water has a hole near the bottom of the container as shown above. So same example up here. As the water decreases, how does this affect the speed at which the water flows out of the hole? So what this is saying is that as water leaks out of here, the total volume of water will slowly start decreasing, go down and down and down until there is no or only water that is below the hole left. So only this water is left. So this water level is going to continue to drop unless it's being filled back up, which it is not. So as the water decreases, how does this affect the speed at which the water flows out of the hole? Well, if you think about your equation, the speed is equal to the square root of 2gh, where h is going to be the difference from the height of the water to the hole. From top of water to the hole. And so if the water level is going to decrease, that's going to change how much height is above that hole. So if you look at your equation, if you decrease h, you're decreasing it by the square root of whatever you're multiplying it by, but that's still going to decrease the speed. Which also makes sense. You just have less water on top of it pushing it through. If the height of the hole from the surface of the water is 0.5 meters. So we are now told that the height from the surface to kind of our hole is 0.5 meters. How fast is the water rushing out in this instance? Well, this would be a great multiple choice style question that all you have to do is understand this rule and plug it in. So then the speed at that location is just 2 times g times h. We know what g is. That's the acceleration due to gravity, and the height is 0.5. So we have 2 times 10 times 0.5, which is going to be approximately 3.16 meters per second. After you take the square root. Don't forget your units. All right, the last example here says a container of water has a hole near the bottom of the container. So here's our hole down here. There's a cup down below that's trying to catch the water. We know that lowercase h is 0.7. We know that capital H, which is the height from our hole in our container down to the top of our cup, is 1.2 meters. Cup is placed so that the water catches it as it's coming out. We know that water does not go instantly down, but it has this projectile motion look here, this quadratic, that's going to go down like this. And so we want to figure out where does that cup need to be placed so that the water is landing inside the cup. So we know that this is acting just like projectile motion. So we have to look at the x and the y separately. And so variable-wise, we have the change in our x, change in our y. We have the velocity in the x, which should stay constant. But our y, due to gravity, should change. We have acceleration in the x, which as long as there's no air resistance, it should be 0. We have the acceleration in the y, and as long as we're on Earth, that should be 10 meters per second, but include the direction. So this is 10 meters per second down. So we have negative 10 meters per second squared. And then time is time is time, which is the same in both of our equations. All right, so we can fill a little bit of information in. The first thing is the projectile, the delta y of our projectile, the vertical change. We know that this vertical change, how far it needs to fall, is 1.2. That's capital H. Now we are going to go down 1.2 meters. So to show that the change is going in the negative direction, we need to make sure we include that in our signs. So we have negative 1.2 meters. I don't know what delta x is. That's what I'm looking for. I know that initially in that y direction, it's going to be coming horizontally outside of that hole. And so we know that the initial velocity in the y direction should be 0. I don't know what final is. I don't know what time is. There is one more thing that I can solve for really quickly here, and that is time and velocity in the x direction. Those are the two things I can get quickly. Let's solve for the velocity in the x direction first, because I know that the velocity in the x direction, how quickly it's coming out of this hole here, is based off of the square root of 2gh. Again, where h is going to be the change in the height of the water from the surface of the water to the hole. And so if I plug this in, I have 2 times 10 times the height. Now this height is not 1.2, but again, it's of the container. So this time we're going to use the 0.7. And when we do this, we should get a speed of 3.74 meters per second. So I'm going to go ahead and add that to my picture here, 3.74. And that should be constant throughout. Now, if you go back to my equation, I know that if I have 3 of 4 variables, I can solve for one side. On my x side, I only have 2 variables. I'm missing 2. So I can't do anything with that yet. On the y side, I have 1, 2, 3 of 4 variables. So if I find what time is, I can then use time in the x direction. That's my game plan. So I'm going to start by saying I'm going to look in the x or the y direction. and I'm going to solve for time. To do that, I'm going to use my third equation here, which says that the change in your displacement, I'm going to use delta y here because I'm looking in the y direction, is equal to the initial velocity in the y direction times time plus 1/2 at squared. I know that the initial velocity in the y direction is 0, so that whole term is going to go away. My delta y, again, is a negative, don't forget that negative, 1.2, and that's equal to 1/2 the acceleration, which we said was -10, times t squared. All you have to do is multiply 1/2 times -10 to get -5, divide that from both sides, and then take the square root. That should get you that the time is essentially 0.5 seconds, 0.49. And once we know that piece of information, we can add that directly into our table. Now we're going to switch gears one more time, and we're going to look in the x direction. We're going to use that to find our delta x. So in the x direction, I'm going to use my same equation here. Delta x is equal to the velocity in the x direction times time, because the initial and final are the same, plus 1/2 at squared. In this situation, we have no acceleration, so that whole term goes away. And we're essentially left with the definition of average velocity, which is the change in position over time. All I have to do is plug in what I know. I'm looking for delta x. I know that the velocity in the x direction is 3.74. I know the time from what I had just found out was 0.49. When you plug those in, you should get 1.83 meters for the distance. So that means that this has to be 1.83 meters away for this setup. As the water drains, which way should the cup slide? So as the water drains, that means that the height of the water will decrease. We know that the velocity in the x direction is going to determine what that delta x is. And we know that that's equal to 2gh. So if we decrease the height, we decrease the velocity. So if we decrease the velocity, it's going to take the same amount of time to fall, because that did not depend on that at all. That was just delta y. Just depended on how high above the cup it was. So as we decrease x, we keep the same time, we must also decrease our change in the x direction. So if that change in x is getting smaller and smaller and smaller, that means I need to slide the cup to the left in order for it to shorten that distance.